I will be the moderator of tonight and then this morning for the ICANX talks with this great, amazing platform. So as introduced, I'm an assistant professor from Sungkyunkwan University in South Korea. My name is Min-So Kim. I'm here very frequently, so I'm sure you know me. And together with me, I'm going to introduce Professor Martin Too, which is he's another famous moderator for the official moderator for the ICANX talks from North Carolina State University. So note that his affiliation has been changed. So, and then today, in this month in September, we have had amazing stars like Professor Jonglin Wang, Professor Nicolas Pepas, and today we have two amazing rising stars, Professor Sangtae Kim and Professor Arka Majumdar. And we are very looking forward to listening to their talks. And then in the remaining 2 weeks, for the rest of the month, we're going to have amazing two stars again. So be here for us next week and in the following week as well. So today here, we are the speakers and moderator. We are all here and for you. And let me introduce Professor Sangtae Kim, who's an assistant professor from Hanyang University. And personally, I've known him like for 8 years, and he's such an inspiring scientist. And then you're gonna see his talk, you're gonna feel that through his talk today. So he did his BS at Berkeley University, and he did his PhD at MIT with an advisor of Professor Ju Lee, who was also a speaker at ICANX talks. And now and then after he got his PhD, he worked as a senior research scientist at KIST Korea, which is one of the famous national research institute in Korea. And now he became a professor at Hanyang University. So let's welcome him with big hands, even though we cannot make noises. Okay, so Sangtae, the stage is yours.
Oh, thank you so much for the introduction. It's really great to come back here to give a talk after last year's Young Scientist Award. And it's personally an honor to present here after seeing my PhD advisor giving a talk in April. That was also a very interesting talk. And I shared my slide, and hopefully it's gonna come up sometime soon. Yes, it's coming up. So let me begin my talk now. The title of the talk is Stress-Electrochemistry Coupling for Energy Applications. And before going into the talk, let me briefly introduce myself, although Professor Min-So Kim gave a great introduction. So as you can easily guess, I was born and raised in South Korea. And then what's interesting here is I went to a high school in Adelaide, Australia. So Adelaide was a great city to be a high schooler. As you can see, there's lots of trees, lots of green gardens. So I could play lots of sports, and that was all fun. And then I moved all the way to the California, United States to go to UC Berkeley for Bachelor of Science in Material Science. There I worked with Professor Lockhart DeYoung and Dr. Mike Tucker at LBNL, learning to do some ceramic processing, basically lots of lab work as an undergrad assistant for solid oxide fuel cells. And then I moved a little bit across the continent to go to MIT for PhD. And there I met Professor Ju Lee to do some work on electrochemical devices, which I will introduce to you today, and a few extensions to it. And then did some ab initio thermodynamics work, which I enjoyed a lot. So overall, PhD, I think, was a great experience, and I hope people enjoy it in general as well. And then I came back to Korea after traveling around all these 10 plus years. And now I work at Hanyang University, Seoul, Korea, to run a small research group here. And as you can guess, my parents were extremely glad when I came back to Korea after traveling around the places that I wanted to go. And my personal secret trip aspiration for next would be going to Africa sometime when I can. So I'm desperately looking for sabbatical chances there. although it's going to be quite far away. Anyway, let's now begin the talk. Today, I will show you some of my work on mechanical energy harvesters, but mainly the theme of my research group would be how stress couples to electrochemistry. Whenever an electrode undergoing electrochemical reaction is under stress, either because of constraint or because of externally applied stress or diffusion-induced stress, its thermodynamic potential will change because of the stress state. And possibly this will also affect the alloy composition and also the diffusion of atoms or ions inside the solid. So these will all be interesting science to explore. And I will introduce some applications based on these effects. So in this talk, I will first briefly introduce what mechanical energy harvesters are and how we can have an electrochemical device to act as a mechanical energy harvester. And once that's done, I will do some similar, introduce some similar work on hydrogen storage and possibly other ongoing research areas. So mechanical energy harvesters in the traditional term indicate basically windmills. You have fluid motion and we transform that fluid motion into useful mechanical work that we can extract. And in the modern era, it becomes more in the human motion part or vibration part. So we would like to convert the mechanical energy delivered by human motions, such as walking or vibrations in the ambient environment, and turn that into useful electricity because that usually gets, the mechanical energy usually gets wasted in the form of heat, vibrations, or sound. And there are quite a few mechanical energy harvesters known, and we can classify them largely into two types, namely the piezoelectric generators, which convert mechanical forces into dipole moments inside ceramics such as perovskites, and then utilize the dipole-induced voltage and current generation. The other type is triboelectric generator, which utilizes the contact electrification of two different surfaces. And once they touch and then get apart, they will exchange electrons and ions at the surface, generating electricity. And at the bottom here, what you're seeing is essentially the current generated by a piezoelectric generator and a current peak generated by triboelectric generator during bending motions. And what I would like to emphasize and draw your attention into today is the width of this current duration. So whenever we bend the device, it's going to generate a current peak, which more or less looks like a delta function and has the current peak width of about 10 milliseconds or less, basically on the order of 1 millisecond. So these are quite unique characteristics of these generators, and they're linked to the fundamental physics of these devices. So it has been really difficult to tune these current durations. And at that point, I would like to bring your attention to what an ideal energy harvester should look like. If we have a mechanical energy harvester with stress input coming in periodically with duration time of T0, then currently the energy harvesters with very fast kinetics generate electric power that looks like this. There's high peak power, but the duration is not so high or large, so that the area under the curve is not very large. And this much amount of time region is not properly being utilized despite the stress being continuously applied there. So that's one issue with fast kinetics generators. And on the other hand, if you have a slow kinetics generator, the device can generate continuous electricity, but it's not fully utilizing the device's potential to generate more electricity because the stress duration is not long enough. So at this point, one can easily guess that the optimized kinetics would look something like this. We would basically want to maximize the area under the curve while the stress lasts in a given input time. And in order to do that, we should be able to tune the instantaneous power, of course, increase the maximum power being generated, and at the same time, be able to tune the power duration so that we can tune the kinetics of the generator according to the input stress frequency. But so far, I have not, at that point, we realized that many of the energy harvesters are not capable of doing that. So we came up with a new type of device called electrochemical generators. The device basically looks much like a battery, but it's utilizing two identical electrodes, in this case, lithium silicon electrodes. And once it gets bent, the electrode interior to the curvature will have compression as colored in red here, while the other electrode will be under tension as colored in blue here. And because lithium ions under compression will envy those under tension, lithium ions will migrate from the compressed to the tensed region, and the electrons will follow in the same direction through the external circuit, therefore generating electricity. So in the more thermodynamic sense, we can plot what happens in that picture just like this. So this is a figure of lithium potential, electric potential with respect to the lithium content in the electrode. And originally, the two electrodes having the same composition and material will have the same potential. But as we apply stress to it, there will be either downward or upward shift to it. And now, if we bend the device, as you see here, there will be generated electric potential of delta V, colored as circle number 1 here. And if the circuit is connected between the two electrodes, lithium ions will be migrating from the more compact, compressed region to the tensed region. And that will continue until the potential difference eventually goes away and develop composition difference between the two electrodes as marked as 2 here. Now, this will continue until the potential difference eventually goes away. But once we unbend the device again, the potentials will now go back to their original state because there's no more stress developed or applied inside the device. And they will now go back to their original black curve there. But this now develops the potential difference in the opposite direction of delta V. And again, if the circuits are connected, lithium ions will now be migrating from the more crowded region to the less crowded region, which was once compressed electrode. And this will now complete the circuit, and the amount of energy generated by this process will be colored as red here. So I came up with a demo device during my PhD studies, and you will now look at a video of the demonstration here. Here's the device clamped, and it's connected in short. And as it gets bent, it's generating current, short circuit current, in real time now. It's reading microamperes. And once it gets bent, it's generating current in minus direction because lithium ions are going back to their original positions. And we can bend this device again to repeat this process for over and over again. So here's the figure of the short circuit current being generated. As we bend the device, there's a peak current and it decays with certain time scale. And as we unbend the device, there's a negative current being generated, and then it also decays with a certain time scale. and we can repeat this process for a while. Please note that the full width at half maximum for this generated current peak is about 3 seconds. So I'll define this generator can continuously generate current for at least 3 seconds. And of course, we can repeat this process for over 1,000 times. I stopped it after 1,500, but I was pretty certain that it can generate continuous and stable current. So at that point, I had one short question, which is, why is it 3 seconds and not 10 seconds or 20 seconds? I mean, the goal here is not to have an exact 3-second generator, but to have a tunable duration for the electrochemical generators. So at that point, I came to question which physical process, in fact, dominates this 3-second kinetics, and whether it is tunable by our designs. So in schematic sense, we are looking at the device here with one electrode under compression, the other under tension. And we can notice that there are 3 major types of physical processes. One is the solid state diffusion of lithium inside the electrode, and then it gets ionized at the surface. So there's an electron transfer reaction. And the ionized lithium ion goes through the electrolyte, which is liquid state diffusion. And then reaching the other electrode, it recombines with the electron. And then there's another solid state atomic diffusion state there. So we can classify the physical processes into lithium solid state atomic diffusion, charge transfer reaction, and then the ionic diffusion inside the electrolyte. But most electrochemists would in fact agree that ionic diffusion is very fast, and it's likely not limiting the entire kinetics part. So I hypothesize that the overall kinetics, which determines this 3-second kinetics, will be limited either by solid state diffusion or by charge transfer reactions. And in typical kinetics courses, we can write down the equations for the modals of these kinetics. So the diffusion limited kinetics will follow the chemomechanical diffusion part, which can be written as a slight nonlinear version of addition of the fixed law diffusion. And what's interesting here is that in the long time limit, after some time, it's eventually going to follow a diffusion characteristic similar to the linear Fickian diffusion. And this is going to generate power law behavior. And in the charge transfer limited kinetics, the Butler-Volmer kinetics dominates, can be used as a model, which basically indicates that the overall reaction kinetics is the addition of forward reaction rate minus the backward reaction rate. And deriving the equations below, we can see that here, the time derivative of concentration is directly proportional to the concentration itself, indicating that this is an exponential behavior. So distinguishing between these two can be quite easily done by doing an experiment for an extended amount of time. So here I am plotting a current peak that I experimentally observed for 600 continuous seconds. And I am plotting the same figure in a semi-log Y figure, where only the y-axis is in log scale. And on the upper right here, I am plotting that in log scale, where both x and y-axis are in log scales. And we notice that there's a linear behavior in the log figure here. And this indicates that there is a strong power law behavior with linear characteristic in the log scale. And modeling the diffusion limited current, basically numerically solving those equations, reproduce this linear behavior quite well. And we can easily conclude that based on these models, we can conclude that current generation is limited by solid state diffusion inside the electrode material. So let's briefly look at what actually happens inside the electrode. So here on the x-axis, I have the electrode distance, and on the on the right hand here, there's a really fast charge transfer reaction going on the corner here. And plotting on the y-axis, I have excess lithium concentration that needs to go away because of stress. And as we see that in the very short time, lithium ions near the surface of the electrode quickly goes away, therefore decreasing the concentration. But after some time, there's a lithium near the surface is almost depleted, and the overall current generation is limited by lithium ions migrating from the end of the electrode to the other side, which is the surface of the electrode, therefore being limited by lithium atom diffusion here. And realizing this, the solution would be easy. I mean, now that we know that the diffusion is limited by, the current generation is limited by diffusion, we can simply change the thickness of the electrode here from 130 nanometers up to about 670 nanometers. And we can indeed observe that the current peak duration changes from 3 seconds, which was the shortest, to about 20 seconds continuously here, like this for the green peak here. So there we achieve what we wanted to achieve, which is a tunable current duration in mechanical energy harvesters. And then here's another brief question that I had, which is, I mean, it's great to have this forward and backward currents coming all the way, but in order to really charge something, say a battery, or with a mechanical energy harvester, one expects to only have forward current rather than having a backward current, reversing the current. So typically in energy harvesters, we typically apply a rectifier diode, which safely removes the backward current, but it's going to cost us about 0.7 volt in generated voltage. And this does not cause an issue in piezoelectric generators because there the voltages are really high, but this device operates in the really low voltage regime, and having a 0.7 volt loss is just a serious issue. So I wondered if we can have a solution for that. And one interesting feature that I came up with was utilizing two-phase reactions in lithium-tin chemistry. So here, on what you're looking at on the left here is the lithiation curve for tin. And you're observing that while we insert lithium to tin metal foil, we are seeing these plateau regions with very flat voltage profiles for large amount of lithium insertion changes. And the reason for that is because lithium-1 tin is in perfect two-phase equilibria with the more lithiated lithium 2.25 tin. And this two-phase region can be utilized. Basically, if we build our generator with somewhere in the middle of this two-phase regime, say lithium 1.5 tin, then the composition difference will now no longer generate any potential difference. Therefore, we will not be seeing backward current. And as we see on the right here, if we make an electrochemical generator based on lithium 1.5 tin, then we're only seeing forward current and very little, almost non-backward currents here. So that was something fun we can try as well. Okay, I think I'm rushing, so let me take some time off. And then The next question I had was, it's great that we can have an electrochemical generator, but some people were questioning whether it's really limited by diffusion and not just surface-driven reactions. So I always have this question in mind, which is, can we actually view or image the lithium extraction upon stress with real-time viewing tools? It would be really cool to actually view this in real time. So I came up with a model system which you can apply, which is two kinds of nanoparticles. One's just typical nanoparticle with only native oxides, and the other is intentionally oxidized in high temperature steam, say at about 100 degrees Celsius. And one will be basically free, almost free of surface oxide, while the other one will have thick surface oxide developed to it. The two were originally almost the same size, basically the same particles. And when we try to insert lithium into these two different types of particles, we will have interesting features on the particles with oxide shell. Namely, as the core tries to expand by accepting lithium into the particle, the shell will be having lots of hoop stresses to it, right? This is just like a balloon. If the balloon tries to expand, if the balloon expands too much, then the balloon's gonna explode because the hoop stress becomes too large for the polymer. So this is exactly what happens. The shell will be undergoing tensile hoop stress and at the same time apply compressive stress to the core, saying that please don't expand too much because I'm gonna break down, right? So we can compare chemically similar. They're both made of tin, but the materials will be under strongly different stress state. So we can compare these two and only do in situ experiments to see whether stress actually drives these reactions. So in order to do that, I found a collaborator who can run this in situ experiments inside the TM column. What he does is he puts this liquid bubble of electrolyte wrapped by two layers of graphene. And then this liquid bubble will survive inside the high vacuum environment inside the TM column. And by shining electrons from the TM column, we can drive the lithiation reaction of the included tin nanoparticles. So let's first look at a video of oxide-free, pure tin particles. We can see that the particle expands slowly but solidly. And then after some expansion, there is not much further reaction going on. I can just play that again to make sure that we can see all the expansions here going on. And we notice that after some time, even though we shine more electrons to it by continuously viewing this window, the particles do not go through much further reaction after being lithiated. And this is the particle with the oxide shell. And at the edges here, you can see oxides with some light contrast here. And we can see that the particle expands just like before. But interestingly, it begins to contract a little bit. And then on the upper left corner here, there's a really dynamic process going on, looking like it's ejecting some lithium out of the material, especially the core. So taking a still images from these videos, I can see that initially the particles will expand up to 180 seconds, and it will begin to sort of shrink and expand and repeat this process for hundreds of seconds. And then it begins to nucleate this void-like feature here. And these voids really dynamically move together to eventually form a single meniscus and a large void here. This is basically like solid state sintering process being viewed in real time. And of course, we would question whether that's real void or not. There can be some invisible, mysterious material such as dark matter, but STEM images could tell us that thickness profile across this line from outside the particle to the shell and through the void and to the core and more tells us that region B, which we claim to be void, is indeed very reduced in thickness, indicating that this is a void. And another question we had was whether this is an artifact of TM beams. So we're shining 300 kilovolt electrons, which is not a normal environment for lithiation. So what we did was we took the same materials, we made a regular battery setup, and then we took out those particles at certain stages of lithiation, and then cleaned up a little bit and viewed these particles here. And we were continuously seeing these voided morphologies for shelled particles here. And at that point, we were convinced that, stress can indeed drive some lithium out of this core, having some really dynamic morphological features inside these nanoparticles when stress, when the material becomes a lot stronger than before. So based on that, we're now designing particle-based energy harvesters where we utilize yolk shell nanoparticles as opposed to regular nanoparticles here. And if we apply hydrostatic stress, the yolk shell particles will not be under stress because the shell protects the yolk from stresses. And therefore, we can generate potential difference and so on. This is currently ongoing in the lab. Okay, so I think I have 10 minutes or so. So let me briefly introduce some of the work that we've done on hydrogen storage and possibly other research areas. So metal hydrides are one interesting form of hydrogen storage. They basically accept hydrogen gas into metal lattice, such as magnesium or palladium, and forms the metal hydrides here. And these are really interesting form of hydrogen storage because they are solid and they can have high density metal hydride hydrogen storage features, but they really suffer from intricate stability issues. So the traditional materials like palladium hydrides are highly metastable, so they easily lose the hydrogen that they store, and we have to put really high pressure in order to charge hydrogen into these materials. This is true for materials like palladium hydrides or lithium aluminum hydrides. And on the other hand, an alternative that people are recently researching are magnesium hydrides. Magnesium is cheap, so people are expecting great improvement on these materials in terms of economic costs. But magnesium hydrides are, on the other hand, highly stable. So once we insert hydrogen to these materials, it's really hard to extract hydrogen from these materials. And currently we require high temperatures above 280 degrees Celsius to extract hydrogen from these materials. So tuning stability of metal hydrides so that we can have optimal charging and discharging behavior has remained difficult for engineering these materials. So one idea we had with a collaborator was utilize stress to tune the stability of metal hydrides. So what we do is we have these cubic shaped palladium nanocubes, and then we thought we could encapsulate these materials with graphene oxides, reduced graphene oxides. And depending on the size, if the nanocube is very small, then we're going to have high regularity in the encapsulation. While if the size is very large or slightly larger, then we are going to have low regularity here. So once the material is encapsulated like this, as we insert hydrogen to the nanocubes, the material, especially the palladium nanocubes, will try to expand, but the encapsulating graphene can apply some stress to it, developing different behavior to it. So here's the data. We are measuring the desorption enthalpy and entropy changes for palladium hydrides. So the reaction is going this way for now. And we are seeing that the unencapsulated nanoparticles have more or less similar enthalpy changes to the bulk counterpart. Bulk means larger particles in the micro scale. And entropy also the same. But under the encapsulation with reduced graphene oxides, we see that as the particle size becomes smaller, the enthalpy change and the entropy change becomes larger. And this indicates that palladium hydride is now more stable as compared to before, indicating that we are pushing towards the optimal optimal stability there. And since I'm running out of time, let me really briefly introduce other ongoing research. One is solid state batteries, where the solid electrolyte can now act as mechanical constraint as we move lithium from one electrode to the other, therefore developing stresses. For example, cathodes, which lose lithium during charging, will develop compressive stress. It will try to decrease in volume, but the contacting solid electrolyte will act as mechanical constraint, therefore generating stresses there. And the other electrode, which is anode, will have the same problem. It now tries to expand, but the contact with solid electrolyte acts as a mechanical constraint, therefore developing stress. And we are trying to quantify the effect of this in terms of battery properties such as cyclability and other things. And the other really interesting part that I am currently actively researching on is thermal energy harvesting. Just like before, instead of applying mechanical stresses, here we are applying thermal gradient to an electrochemical system, otherwise identical. And this temperature gradient is going to drive oxidation reaction on the hot side and reduction reaction on the cold side, therefore being turned on just like charging batteries by thermal gradient and not electricity. So these devices, I'm hoping, can be useful in scenarios like nuclear reactors under accident, where there's no other source of energy than thermal energy because heat is actively going up. And then somehow these devices can suddenly be turned on because of the thermal energy and generate the necessary electricity to run the pumps and so on. So with that, I would like to summarize my talk. We work on stress or temperature gradient driven electrochemical reactions and some other variants in hydrogen storage materials as well. We are basically interested largely on how the thermodynamics of stress and temperature can affect the electrochemical systems in terms of potentials, compositions, and diffusion parts, and possibly utilize them in useful devices. So with that, I would like to thank the sponsors who are NSF, Honda, National Research Foundation of Korea, KIST, and Samsung as well. And I would also very much like to thank my PhD advisor, Professor Julie, and direct collaborators in the work and friends as well. If you have any other questions or comments, please write me an email. I am very quick with emails. And more information on the group can be found in this homepage. So thank you very much for your attention, and I would like to end my talk and take questions later on.
Thank you. Thank you very much, Professor Kim, for your presentation. Now it's my great pleasure now to introduce our next speaker. Let me see. It's my great pleasure now to introduce our next speaker, Professor Arka Majumdar. He's a professor at the University of Washington, and he's not only a professor, but also an academic entrepreneur. He has earned so many awards that I'm not going to go through. He has several Early Career Award. And of course, he was the ICANX Young Scientist Awardee last year. That's why he's here. And he has done amazing work on Meta-Optics to a point that it's getting commercialized. His journey started in India, academic journey started in India, and from there he came to the US and has spent time at Berkeley and Intel Labs prior to joining University of Washington. Without further ado, let me welcome Professor Akama Majumdar to tell us about his work.
Thank you. Thank you, Martin. Let me share my screen. Just want to make sure. Okay, it goes there. Great. So thank you, everyone, and thank you for inviting me. Yeah, it's almost has been, I think, 9 months after we gave the final presentation for ICANX. As Martin mentioned, I'm from University of Washington, Seattle. I'm from Electrical and Computer Engineering and Physics Department. And what I'm going to talk about is what we call as software-defined meta-optics. I'll tell you what does meta-optics mean, what does the software-defined mean. So if you have most of the work that I'm going to present, you can find the papers from my group website. This is my email. So if you have any questions about this talk, or there are a few other things going on in the lab, just feel free to send me an email. So yeah, I think get started. So acknowledge my team and funding. So this particular work, Meta-Optics, has a lot of industrial relevance. So we actually got a lot of funding from both federal funding as well as funding from the company. And we also collaborate with various different people on the computational side, from of course from University of Washington, but also Princeton and MIT. So before I go into talking about this particular topic of software-defined meta-optics, let me tell you a little bit about what is going on in my lab. So my lab is really interested in understanding what is known as this light-matter interaction. So the interaction between electrons and photons in a very, very small length scale. And to achieve that, we design and fabricate various nanophotonic structures. So these structures have features on the nanometer length scale or sub-wavelength length scale, which really allows them to focus light or confine light spatially and temporally in a very small mode volume for a large amount of time. And then we put new materials on those nanophotonic platform. These materials include like 2D material. We work with phase change material, colloidal quantum dot, organic chromophore. And idea is that when you pattern this surface, put this new material, what kind of new effect, new physics you can study. But my lab is very interested in figuring out with those new science, what can we do, right? What kind of application it can enable. So one of the applications that we are very interested in, kind of quantum many-body simulation with correlated photons. So many of you know that there's a lot of work going on in the quantum simulation, the atomic cold atoms, ion traps, superconducting, they are leading candidate. But the photon has some benefit. It can be room temperature. You can actually use photons very easily to scale up. So can we actually engineer photon-photon interaction? That's the question we are trying to answer. In another work in collaboration with Intel, we are trying to develop this hybrid integrated photonics. So we are trying to put phase change material on silicon photonics and trying to see if we can increase the bandwidth, data rate for data communication. We're also interested in what should be the main kind of topic of today's talk. Can we actually make very, very small sensors, very small image sensor using this nanophotonic technology? And it turns out that when you make this kind of system small, fundamentally, nothing to do with nanophotonics, fundamentally from diffraction, your performance is going to go down. A small system has several problems, and there is when you scale the lens smaller and smaller, your space bandwidth product is going to go down, and your performance is going to get worse. And what we ask ourselves, okay, is it possible to use computational backend to improve the image quality or to improve the imaging performance? So this is what going to be today's main focus. But then we realize that we have this kind of nanophotonic system and we have a computational backend. Together, can we actually start thinking about doing sort of optical computing? And that's kind of what will be like some part of the talk also, that can we use this nanophotonic element, in this case Meta-Optics, which I'm going to explain what it is, and a computational backend together to create a new sort of maybe optical kind of neural network, a neuromorphic computing. So that's kind of what the goal. I'm going to focus primarily on these two topics. Okay. So what's the main motivation? If you look into today, the cameras are everywhere. We all are carrying one in our phone, but many applications, including like autonomous navigation, mixed reality systems, smart home sensors, also like next generation mobile photography, you require more and more kind of cameras or different kind of cameras. You can think about also applications that is in biomedical field, endoscope, very, very small microscope for brain imaging. So all these applications require even smaller or different kind of camera. And not just camera, these have given rise to explosion in the field of computational imaging and computer vision. These are like two of the most, I would say, exploding field in the computer science and engineering. They are using a lot of machine learning technique, a lot of deep learning technique. You probably know that this whole rise of deep learning, the ImageNet, came from computer vision community because they did this image classification, which really falls under computer vision. So what are those two? What is computational imaging and computer vision? So if you think about a typical pipeline, so this is a very abstract way of telling that what computational imaging and computer vision do. In computational imaging, the idea is we want to make a cheap, small camera. So we use a low-end optics. So when you say low-end optics, that essentially means, like, let's say you're using only one lens. So if you ever open up your cell phone, you will see there are like 8 or 9 lenses. But instead of that, maybe you're going to use only one lens. Sometimes people are using even like a random surface, a disordered surface. And goal is, of course, to capture this scene. So what you're going to capture, that something doesn't look very good. But then you use computation. You know that using Fourier optics, that we know how the light wave propagated or ray propagated, you can computationally reconstruct to get back the image. So generally in your cell phone, you use optics and you go from here to here, but you are using a low-end optics to get here, and then you do computational reconstruction. Now, having said that, there is almost no imaging system today that doesn't use computational reconstruction. So your cell phone already is doing a lot of computational reconstructions, and I can give you examples what they do. But this is kind of what the idea is, that we capture something that may not look good, you put on some computation. For computer vision, the idea is to capture something that is as high, like a highly faithful replica of the same. So that's why we're calling it high-end optics. It can be mini optics, large optics, bulky optics, but you want to capture a scene which is really, really good. And then you do computational feature extraction, and then you do pattern recognition to make a decision, like maybe facial recognition of some other kind of problem. And in these two fields, if you look into the current research, it really falls into this computational part. So there are a lot of work going on in the deep learning, and many of these algorithms are based on deep learning. The optics is fairly untouched, in the sense that the optics are generally commercial off the shelf or some kind of random medium. But if you look into now, you probably heard in many places, the deep learnings are fairly power expensive. So often, uh, the deep learning and a computation algorithm takes, takes power. It also creates a latency. So for real time, low power application, relying purely on computation can get very expensive. So can we actually solve it? And that's kind of really what we wanted to start with, that can we reduce the computational complexity of this kind of sensing problem, the computational imaging and computer visioning sensing problem using free space optics. So what do I mean? So let's start, give some example. Let's start from this. These are my scenes. And my goal is to go to the right hand side. So either I want to capture a very good replica of the scene. Maybe we want to capture depth. Maybe we want to identify where the cars are, or maybe we really want to identify what this whole image is, or maybe what the whole face is. And the plan is we want to bring it to an intermediate stage using optics, such that when you turn on our computation to go back to the final results, the complexity of this computational algorithm or computational block is lower. So you essentially have low power and low latency, because you are actually bringing optics, which are essentially passive, and things are happening very, very fast. The light, the time it takes for light to travel to this stack is like less than nanosecond or even less than picosecond. To bring it to an intermediate stage, which are more amenable for computational post-processing. So how do you do that? So of course, we need to do computational design of optics. And that's a big departure from the way things are happening in computational and computer vision. Here we are going to design these optics point by point or pixel by pixel. And you can think about voxel by voxel, which is a little bit difficult to fabricate. But we are going to design these optics at each point using computational technique. And then can we actually co-optimize the optics with computational algorithm? So not just optics, we are actually going to figure out what is that optics that makes the computational lower, and vice versa, that how does, what kind of computation makes the optics also simple. Okay. Now, these ideas are not necessarily new. People have thought about even back in 1989. Maybe not exactly in this form, but really this idea about optics to do some sort of computing or reduce the computational complexity. This particular paper, first time into the MIME knowledge, actually talked about this co-optimization of end-to-end design. But for the reason, uh, as we'll see, that one of the problem of this kind of optics has been these are very bulky. And we asked a separate question, which to the best of my knowledge, no one has really asked, that can we actually also simplify optics using computing? And essentially there are work where people have done like put all the work of the optics in a computation. So when you're doing random medium, disordered medium, essentially this lensless imaging, then you're doing everything with computing. But in our case, we are saying, no, we still have an optics, but maybe we can simplify some of the optics and add with the computation. And that's why we call it software defined, because that's exactly the idea of software defined radio. In software defined radio, what happens is that you put bulk of the complexity in the software, you make your hardware somewhat less complex. And I'm going to give you an example that how actually computing can help to make the optics maybe simpler. There is a strong connection about this kind of pipeline with deep neural network. And let me kind of make that clear. So if you look into deep neural network in today's world, the way it works, we have some kind of images. These are in software. And then you want to classify. That's the most important problem that everyone is working on deep neural network. Generally, you have a linear, nonlinear, linear, nonlinear layers. So we have a cascade of linear, nonlinear layers. So as you can see, if there's a nonlinearity, you cannot really just collapse this linear layers. And that's how most of the software-based deep neural network works. It turns out for optics, getting this nonlinear activation is very hard. So can we actually think about a new kind of architecture where we bring a lot of linear layers in front, then we do a handoff to the nonlinear backend, and then we have this kind of nonlinear linear layers. And then we can implement all those layers using optics, and then we have the software. So essentially, we have an optical front end that does a lot of pre-processing, and then we hand off to software. How do you make these things are actually not, how do you train this kind of network is not trivial. We have developed a lot of algorithms, which I don't really have time to go over it. Also, if you are someone working on deep neural network or deep learning, you might recognize that all those layers linear, so it can be just a single matrix. Why do we need multiple optical layer? At least why I'm drawing it as a multiple optical layer. The reason is just because you have a single layer of matrix doesn't mean you can always find a single element or single optical element that can do that kind of multiplication, that kind of matrix operation. But those are more details. But essentially, what I'm going at, that the deep neural network architecture, we can rethink. It's a completely different kind of architecture. This kind of architecture will be very difficult to train, and you have to develop new algorithms. But this kind of algorithm really take the advantage of optics, because you are essentially doing a lot of linear operation and having a drastic reduction in terms of dimensionality. I'm going to show you some initial results on supporting that as well. So I think, as I mentioned, these kind of ideas are not new. People have looked into it for a long time. But the reason this never really kind of got a lot of attention is because the optical elements, free space optical elements, as we all know, are large, bulky, misalignment prone. So can dielectric meta-optics provide a solution? And so what is dielectric meta-optics? So dielectric meta-optics, in my opinion, are essentially sub-wavelength diffractive optics. You have we all know about diffractive optics in this kind of lenses. This curved surface provide the focusing. So light incident at different part of this lens is going to bend because of different curvature. But if you think about Fourier optics, light incident at different part of this lens undergoes a different phase shift. So once you think about phase shift, anytime it reaches 2 pi, you can bring it to 0, and you can create kind of what is known as a kinoform diffractive optics. They're difficult to fabricate, so but this continuous profile you can quantize, and you can get a single stage diffractive optics or multi-level diffractive optics. So you're really using different thickness to give different phase. So you need multi-stage lithography to fabricate this kind of structure. What happens when you go to sub-wavelength scale, you can actually provide different phase shift just by changing the lateral geometry. So you can fabricate that using a single stage lithography. And secondly, comes from very simple like freshman physics, that if you have a periodicity of, let's say, A times sine theta is lambda, that's where first order maxima happens for a grading. So you can see that if if A is less than lambda, then sine theta becomes greater than 1. So you don't have any higher order diffraction. Okay. So that's how kind of, in my opinion, this is the two main benefit of dielectric meta-optics, that you can fabricate them with single stage lithography, and you don't lose light in higher order diffraction. You can put everything in the 0th order diffraction. Okay, so how do you design this meta-optics? So there are we have developed a lot of tools, and not just us in the community. There are many tools to design meta-optics. The more simple and the one that we more primarily use starts with we start with a periodic structure of some scatterer. In our case, we either use cylindrical scatterer or square pillar. And then we run a lot of full wave simulation using rigorous couple of analysis. And our goal is to see in this periodic structure, if you have the same thickness, same periodicity, by changing the diameter of this scatterer, which is essentially duty cycle, can we get covered 0 to 2 pi phase shift? As I mentioned, by changing the lateral geometry, we are changing the phase. And can we also get good transmission? So once you find this parameter, this is the good one. We also identify the phase distribution that we want to implement. And then we discretize the phase. We find out that, okay, what is that Z height or the phase? We find that phase, we find the getting parameters, and that's how we can create our meta-optics. So you can see this is kind of one of the example of meta-optics. You have an underlying square periodicity, but the size of the scatterers are changing as we are going across this XY plane, and each scatterer is going to give you slightly different phase shift, and that's how you make a meta-optics. Okay, so with this kind of background, I'm going to talk about 3 experiments where we are really using computation and meta-optics together to do something that could not be done just with meta-optics. Okay, so let's start with the first aberration-free imaging with large area meta-optics. So what is optics good for? So the most of the time we use optics to capture imaging, and we capture colored imaging. That's what we use our cell phone cameras for, right? It turns out meta-optics has very strong chromatic aberration, and it's nothing to do with meta lens per se. Any diffractive optics has very similar chromatic aberration, very strong axial chromatic aberration. So light at different wavelength focuses at different point along the optical axis. So this is the actual measured result for green, blue, and red Meta-Lens. And what it looks like, if you want to capture this scene, you are going to see something that looks like that. So how do you solve it? There's a lot of work on dispersion engineering. There are two at least work I'm going to mention. One's earlier work, and they use complex meta-atom engineering to solve for phase and group velocity dispersion. They require very large parameter search, generally polarization sensitive. They cannot be applied to large area. People actually have shown it that they will be either limited in aperture or numerical aperture, and the fabrication of this kind of meta-atom becomes almost impossible. So what we came up with our solution is, if you think about a current meta-lens focuses light at different point for different wavelengths. So instead of a point, is it possible to focus them along a line? So if you focus them along a line, we can find a plane where all the wavelength reaches the sensor plane exactly the same way. And we do that using what is known as this extended depth of focus meta-lens. We are extending the depth of focus instead of a point, we are extending it to a line. And then we computationally post-process to get the image. And I'm going to discuss exactly what are the requirements in a bit. But that's the basic idea. And the way we did that, we added what is known as a cubic phase mask. So we added a cubic phase mask to our phase. So this is our hyperboloid profile. We have a cubic one. So when alpha is equal to 0, you get like what it looks like, something like Fresnel lens. But when you have a different alpha, you get an asymmetry. And this asymmetry is key to create this kind of extended depth of focus. So how does the PSF and MTF look like? So the experimentally measured result. So you put alpha equal to 0 and you put your sensor at green, it's very well focused, red and blue gets blurry. But when you have some alpha equal to 55 pi in this case, we added some cubic term, you see that they don't look like lens at all, but they look very similar. And we're showing 3 wavelengths, but in between wavelength, they're also very similar. So that's one of the important points, because when you are capturing images in a colored camera, even though you have a color filter, these are not narrowband filters, they are fairly broadband filtered. So almost all the wavelengths are reaching the sensor. So now, if you take a Fourier transform of that and get the modulation transfer function, and modulation transfer function essentially tells you that these are the spatial frequency of the object in the x-axis, and what is the weight by which that spatial frequency gets multiplied when we capture that in the sensor. So for a meta-lens or hyperboloid meta-lens alpha equal to 0, you get nice good performance for green, but red and blue, you get much, much narrower. And this is very important because these spatial frequencies are getting multiplied by 0. When something gets multiplied by 0, it's 0. That you cannot get back. And that's one of the things that often gets misunderstood in the community. Computation is not magic. It can only give you what your hardware is capturing. Okay, it can improve it, but only based on what your hardware has captured. And meta-lens cannot be deconvolved by computationally to get back the image. In our case, as you can see, of course, we take a hit, like our MTF doesn't look like diffraction limited, but we have non-zero component for a very large spatial frequency. So if we know what it's doing, we can always multiply this spatial frequency with this kind of values and get back the diffraction limited performance, at least till when it's not going to 0. I mean, in real experiment, is limited by the noise, but the overall point is that you need to make sure all the PSF are same, and the PSFs has or MTFs has non-zero value till a very large spatial frequency, which you cannot do with hyperbolic lens. So how does the imaging look? So this is a very early on, it's almost 4 years back, our imaging. I'm going to show here, like this is done with a hyperboloid. You can see the skin color, the sky color doesn't look good. All the stems gets blurrier. We can get by the sky color and the stems. Okay. But there is no question this image quality is very poor. So there's some of the work came from Harvard, some from China, and also our group. Our image quality is very to kind of very highly emphasize that whenever we are comparing image quality, it has to be done under the broadband ambient illumination using a colored camera. Anytime someone is showing a black and white imaging, calling it broadband, it's a little bit misleading, because we have seen that the whole problem of chromatic aberration comes only when you are trying to preserve the color information. So You need to use a broadband illumination, not 3 lasers, and you have to have the color filter, because that's the quality that we do it in the cell phone. When you image from outside, you have a color filter in your sensor and you are doing with ambient light. So this image quality is very poor. And this is kind of an important point that we asked ourselves, that if you look into any kind of work in Meta-Optics, people start with the cell phone. So if we cannot reach cell phone quality imaging, or at least our image quality is so much poor, how can we say that Meta-Optics will be any better? So that's kind of the question we kind of asked ourselves, that is it possible to get good image quality? And we spend a lot of time. And I say, like, what is our design insight? Our design insight is we want to make sure the MTF for each color remains same. The first zero of the MTF appears in the large spatial frequency. And also what we realized, that we really want to have larger volume under this Meta-Optics curve. But now, as I mentioned at the beginning, we have a lot of computational tools. So we can define a figure of merit for our optics and use what is known as inverse design, or you can just call it optimization. And that's kind of what we did. So we actually put together a framework where we have a model for Meta-Optics. We have a computational model, and we train this whole system with neural network. And this PSF, when you are doing it, we are essentially trying to make sure that the PSF remains same for different wavelength, different angle, and you have a large area under the curve. And this requires a significant amount of algorithm development, that how do you actually make the Meta-Optics run very, very fast? Like, because if you think about Meta-Optics, it has a trillion or maybe like millions to billions number of scatterer. Each scatterer has to be modeled with the full wave simulation. Then how do you make the large simulation? There has to be a multi-scale algorithm development, which we did. And this is the result that we got. So this is a compound optics with 6 lenses. So this is essentially same as the ground truth. And this what we can get with our Meta-Optics and computational imaging. So image quality is significantly improved. Like, of course, it looks like that way, but we also have measured parameters like structural similarity, PSNR, to prove that. And this is done with a 500 micron aperture, f2 lens. So that means your focal length is 1 millimeter. This is one of the largest aperture when we published this last year. And we have field of view 40 degree, but we pay a penalty. We have a computation, so our latency is 36 milliseconds. So this is in 2021. We also explored in this particular paper, which came out in Nature Communication, that we can also use less expensive computational backend. So right now our computational backend actually has, which we call feature propagator, is essentially a deep neural network. But we can do that using Wiener deconvolution or some kind of other one, and we can still get fairly high quality imaging. And that's important because, as I mentioned at the beginning, right, we are looking for low power, low latency. So we are designing a new optics that can help, but we still don't want to put a lot of burden on the computational backend. Okay. So again, so some more results from that time. So for 2 millimeter, we can get full color imaging. So this is the ground truth. This is the colored imaging. Can we do even larger? So this is a 1 centimeter meta lens that we fabricated. We can actually package it, and then we directly put it on our camera. And this is how the image look like. I have a small video. This is taken outside the university in the ambient light. So you can see that you can, like, this is image quality is still not there, and that's something that we are working on. But in the ambient light with the full color, you can see the fountain, you can see different flower, the building, the sky, and your color is preserved. This is the first time someone is measuring in real world video using Meta-Optics. Okay, we have a very simple computational backend here, just a Wiener deconvolution. So can we go for the other wavelengths? We're working on the thermal wavelength. So these are the 2 images. One is for hyperboloid and one is this end-to-end design Meta-Optics. And in thermal, you can actually see what this end-to-end design is doing. It's essentially adding a lot of extra component on the interference in the circumference to actually solve for aberration, solve for geometric aberration. And these are kind of some of the imaging that we did with thermal. So some of this idea can be very easily translated to thermal. And that's one of the benefit of using this kind of non-meta atom engineering, because the meta atoms finding this kind of scatter are very, very easy, and then you can use the computation. Okay, I'm going to quickly now talk about two other things where I guess you can see like how the optics can be simplified. So one of the thing is this tunable lens. So tunable lenses are very important. And one of the idea we had pursued for a long time is one known as an Alvarez lens. So the two cubic element, if you place in front of each other and you laterally slide them, you can get a tunable focal length. But this actually turns out to be very difficult to get a large focal length tuning. We spent a lot of time developing this MEMS technique, and we only got a 3 mm tuning. But again, we asked ourselves, can we use computation? And the answer is yes. So we can actually use this extended depth of focus meta lens. So you can see this meta lens actually integrated with a camera. And we are essentially changing that object. So when you change the object, as we know, for a lens, things are going to get blurry. In our case, as we have an extended depth of focus, we can actually capture the information and computationally correct it and get crisp image for with our approach. So we essentially can get varifocal functionality, which is very difficult to get using physical hardware, but using software. Okay. Anything else? Can you do other sensing modalities? So one of the things is depth sensing. There's a lot of interest for various different application. And our idea was we'll make one Meta-Optics that is depth invariant, which is essentially extended depth of focus, and another Meta-Optics which actually changes with the depth. So if you make these two Meta-Optics, this kind of idea people has been done before. So they need many optics. This is kind of the setup that came from Rafael Piston's group. You can see that they have a 4F imaging, they have an SLM, and this SLM, they toggle between either this extended depth of focus or depth variant response. We actually collapsed everything to just a single surface. We have two elements. This two element, one of them, this one is depth variant, this one is depth invariant, and we essentially capture two images in our sensor. So one of them is this depth invariant one, from where we can get the actual 2D image. And using the 2D image with this depth variant response, we can find out where the PSF is. From the PSF, we can find out the depth. And there is a little bit more complexity in the computational algorithm because these two are not exactly collinear. So you have to kind of take into account that, and those are details in some of the earlier paper that we wrote. We can also use very similar technique to do computational spectroscopy. So in a recent work, we showed that this kind of double helix point spread function, actually the point spread function, the two blob that we have, essentially it looks like two focal spot, and the two focal spot rotates. So you can see here, like in one wavelength, the focal spot looks like this, the second wavelength, it goes like this, third wavelength, it just rotates. So essentially you have a very strongly wavelength dependent response. This is going against the kind of full color imaging. And we use kind of a large area Meta-Optics in silicon, and we showed that we can get a very high quality spectral reconstruction with our line width of only 5 nanometer. Okay. Finally, we talked about object detection, that can we actually use object detection? And this is kind of a very important problem in my mind, because can we do optics? Like, can we use optics for computing? That's the question we asked. And is there a benefit of doing that? So to the best of my knowledge, no one has shown exactly a head-to-head comparison between an electronic and optical system. Optics, of course, do things faster, but there are like ultimately computing is a system level problem, not a single block. So what we propose this platform that we have a display, we send it to a Meta-Optics, that's my optical front end. You capture something and then you send it to camera. And we used our co-optimization algorithm to find out that, okay, these are different Meta-Optics that we designed. So what is happening here, this Meta-Optics, from this Meta-Optics, we just capture one data point. So whatever sensor is, we just average out, and that one data point goes to the electronic backend, either 4 or 9. So essentially what we are saying, the Meta-Optics encodes the information in certain number of points, and the certain number of points goes to an electronic backend. That electronic backend, the complexity of the electronic backend depends on that how many data points are going in, and their power and latency is going to scale with that. So basically, if you start with a one data point, it will be much significantly less computational expensive than if you start with 100 data points. And then we co-optimize each of this backend with the computation. And then we essentially compare that if you take the image without any Meta-Optics, we can always just create a single point. We basically add up all the image, all the pixels, or create a 2x2 image or 3x3 image computationally and put it in the computer. That will be purely software. And in the other case, we are essentially putting a Meta-Optic. So we make sure that our power and latency of the electronic backend and optics plus electronics are same. And we asked ourselves, is there a benefit? And what we found is very interesting. What we found that when you have, this is the number of pixels that going into the electronic backend, it's not surprising that it's increasing. As you have more and more data, you get more classification accuracy. But when you keep a large number of pixels, you actually have no benefit of electronics over this hybrid optical neural network. So you can actually get a very, very complicated electronic, very, very simple electronic neural network to do a lot of things. And these are done with the MNIST dataset. And then at an intermediate regime, as you can see here, that as we are having less and less data, less and less input, electronics start falling off much, much quicker than the optics. So optics actually has some advantage in some intermediate regime while you have still fairly good accuracy, but you are doing better than pure electronics. And then it falls off again. So in theoretically, this is the plot it should be. It falls off, we believe, is because of the experimental noise, because when you are having a single pixel, you have a huge amount of noise in experiment, and that's why it's kind of falling off. So we are still kind of working on to kind of figure out how best this thing works. But overall, it really looks like that there are, for the first time, people are showing that there is actually a photonic advantage when you compare against exactly the electronic backend, an electronic software-based neural network. At the end, I think what I'm going to say, like the synergy of computation and Meta-Optics, where we computationally design Meta-Optics. I just showed most result with the single Meta-Optics. You can also do multiple Meta-Optics. That's something we're working on. People are also looking into volume optics. So with 3D printing, you can make like things that are changing also in the Z direction. So this computational design of Meta-Optics with computational post-processing really opens up ways to do things that we could not do before. Right? We can really reduce the latency, reduce the power consumption, while at the same time get a similar performance in a very, very small form factor. So that's kind of what I think is really the promise of the technology that we are developing, and we are really just scratching the surface. I just show you some example. There is a lot more work to be done, and can we really beat an electronic system? Can we really beat the state of the art? Is something that we have to still work on. And as Martin mentioned, we actually also are trying to commercialize some of this idea through a startup. So here also, like, idea is very simple, that instead of creating this kind of bulky optics, putting everything on the optics, can we use simple optics, computational backend together to do this kind of image and sensing modalities? And some of the applications that we think are very important and needs to be solved. One of them is, of course, mobile photography. We all know there is a bump into it, and we really want to kind of get rid of that bump using this kind of optics, innovation in the optics and computational backend, but also endoscopy and angioscopy. So we have a lot of work going on that when you make this kind of optics really, really small, you can actually create, reduce the tip length of current endoscopes that essentially can go into various different locations that you cannot really reach. But using the same kind of idea that we have a Meta-Optics and computational design. So I'm going to stop here, and yeah, I'll be happy to discuss, happy to take any questions that you have in the discussion section. Thank you.
Thank you very much. Very interesting talk, and very happy to have you back, both of you back at ICANX. I'd like to switch into the questions. We have two questions from the audience. One is for Professor Kim. Thank you for the wonderful talk and insights. My question is, how does the composition of the surface change as the lithium diffuses across the interface, especially in the particles that form voids?
Thank you for the interesting question. So I understand the question is asking how the composition of the particle surface will change as the particle forms voids. And I could not show, but we did some electron diffraction studies to identify, well, we tried to at least to identify the phases that exist inside the particles as we observe these morphological changes in the particles. And what was interesting was that typically in lithiation theory, people would expect that this entire particle will go through single phase transition from one phase to the other as it gets lithiated. But what we were seeing in these stressed particles is that they actually go through multitudes of phases inside a single particle. So we were observing like pure tin along with lithium oxides, lithiated tin, sub-lithium tin, and so on. So it was not, we could not exactly identify experimentally what exactly is the surface composition of the particle, but based on those evidences, I can expect that the surface composition will be mixed with some lithium oxides, of course, converting tin oxides into lithium oxide and tin islands inside. And those tin islands inside will have mixed lithium composition states as they form voids. That's the best I can answer for now.
Thank you very much. I think that the person who asked that will be happy to hear that answer. The next question is for Professor Majumdar. Again, great talk on application of metamaterials. Given the current rise in mobile phones, I think this person wanted to say mobile phone prices. Do you expect these meta lenses to lower the cost, or will they be more expensive than current technology?
What I say to like people when people ask about cost, right? When people went to moon and they said that this is the small step, is a giant step for humanity, it was wireless communication, right? So wireless communication was there back in 1960s, but cell phone did not existed, right? So the benefit of semiconductor technology, it can give you extremely cheap, but I don't think that's really where metamaterial is going to do it. It's probably going to be maybe thinner cell phone. That's one of the application. I don't think the cost is going to be any lower or more with this kind of stuff, but making maybe thinner laptop, but also like there are applications. I talked about cell phone because it's easy to kind of understand, but for example, augmented reality visors, they have a lot of sensors. So all those sensors requires very small form factor. And the whole point that what we wanted to see is if we cannot actually solve that very simple problem of imaging, like imaging is in some way the simplest thing that lens can do. How can we even argue that it can solve other problems? That's kind of what we went with that. But really, I feel that it's essentially going to be better rather than like cheaper or expensive, more expensive. And it's really like if we do it the semiconductor, the cost gets amortized over all the cell phones, and you are going to have very, very cheap. So there won't be like any extra cost than what we have in the plastic lenses.
Very good. Alice, thank you for the answer. Alice, do you have questions from the audience?
A lot of audience are here. Okay, we can go to the final discussion for the questions. Hi, Martin. Can you hear me?
Yeah.
Okay.
Yeah, we can hear you.
Oh,
There are questions from the audience.
oh yes, we have. Yeah. So,
Go ahead.
yeah. Okay. Can you? Yeah. Okay. Please, Rafa.
Hi, hello. Hello, hi, Mr. Matuda. Yeah, it's a pretty nice talk. So, oh, hi, Kim. Yeah, yeah, I got one question. So my question is like, how is because I saw that the aberration control for the lower end case for your meta lens is pretty good. And how about the control for the high NA? And another question is like, is that possible to combine some other phases to pretty much like achieve some super resolution or something, maybe like combine some super oscillation phase or something like that? Is that possible for the meta lens? it's pretty nice, pretty nice answer. And I got another question. Pretty much is a really old question. Everybody may ask you. So how do you solve the efficiency problem, like the loss from the metamaterial? Oh,
So basically, there is no loss from the material absorption. You do have some focusing efficiency problem, and that's why we kind of need to that's why we do inverse design to have the highest efficiency possible. But we do lose some energy also in the computational, like it's not like perfect. So you don't get a diffraction limited performance in all the wavelength. But I will point out that I don't know, I have an iPhone. If you take an image in a low light condition, it will take some time, right? They are doing computational imaging in the backend. So what I'm getting at is computation is not free. It takes some things, but people are already using it. So these are already in your phone, is already in your laptop. But we don't have any absorptive loss because we are using transparent material. There is no metal here.
That's great. Yeah. Sorry, I pretty much I maybe missed the first several slides. I didn't realize that you used the dielectric one. Yeah, pretty
No
good.
worries.
Yeah.
Okay, Martin. Yeah. So pass to you.
Okay, thank you. Thank you very much. Thank you for the questions. So, Miso?
Yes, I'm here. So are we gonna do the discussion further, or yeah, are we gonna keep the discussion?
We need to go to the panel.
Oh, okay. So this is for questions, and we can continue the question and answers again, and then we can keep doing some discussion for both academic and personal stories, right? So which one would you prefer? So I can start. So
Yep.
I have one technical question for Professor Sangtae Kim. So you showed a very nice TM, the videos, and then so that we can see the all the moving and diffusion part. So I was a little bit wondering because since the TM is just shows us the local images or the videos of the whole part. So how would you observe the overall performance of the whole materials or the whole device samples? Would there be any like insight or I know this is a challenging question, but
Yeah, it is indeed a difficult question to
I'm
answer.
so sorry. Okay.
That's okay. But the question goes back to a little more fundamental question of whether this stress electrochemistry coupling persists in scales greater than nanoscale. For example, the video was really exciting in the sense that we could observe how stress can move lithium from one part of the particle to the other. But I wonder if we will ever observe that in bulk scale particles, because as we know, in the bulk scale, materials will deform first as we stress them. For example, there will be, say, dislocations nucleating and microstructural issues coming up and things like that in larger scales. So the question, going back to the question, I think in the device scale, I think observing these drastic changes will be different, well, difficult. And that would actually tell us a little more about how we should design these devices. Essentially, we should rely on nanomaterials because they will be stronger and they can sustain more stress and potentially more elastic stresses. So I think the success of these devices will rely on those properties of nanomaterials rather than their bulk counterparts. I think I'll answer up to this point. Hopefully this
Thank you very
answers your
much.
question.
Yeah, I'm sorry that I gave you some challenges though. And yeah, the local phenomenon from the TM images and the macro scale performance is always an issue like to discuss. So thank you. Nice answer. So I'd like to ask a question for both of you. So since there are so many young scientists out there listening to you right here, so I'd like to ask what would you advise to the future professors or future scientists of kind of what to prepare when they're younger than you? So like, yeah, so any advices? So probably Arka first, so that Sangtae can prepare.
Sure, sure. I think like I mean, I feel that many of you are way more well prepared than when we were. I am seeing it every time the applicant pools that comes in is stronger than when I applied. So it is getting more and more competitive. So my main advice is that, of course, you have to kind of work very hard. One thing that I think is kind of important to recognize. So we feel that when we are a kind of younger, we feel that, okay, maybe making small silly mistakes are okay, because that doesn't tell you that you are actually going to, that doesn't tell you that you are not intelligent. But at the end of the day, I think when you are getting into really kind of research, you are doing something unknown. So only way you can go ahead is by not doing those kind of small mistakes. If you're making this kind of small mistakes, pay attention and make sure that you don't repeat your mistakes. I mean, I will say like that will essentially make things do faster. And then you can try many different things, because in research, things are unknown. You just have to try many different things. I mean, there is really no other way to do the research. So that's, I always say, like, I mean, one of my advice. And other than like, I think like you guys are very well prepared. I mean, you were trying to like talk and like you can actually connect to the whole world. I mean, that was like almost impossible, like when we were growing up. So yeah.
Oh, thank you so much. So less mistakes. Okay, Sangtae, again
Yep.
to you. Sorry.
Okay. I fully agree with Arka that the younger generations are overall doing a lot better than well, my generations, I feel. But one thing that I think it's was important or very helpful to me at least was to try to do more discussions with people, like whether they're in your disciplines or whether they're in completely different random disciplines. Trying to explain your ideas in plain languages by giving talks to audiences of different stages, and then answering their random questions, whether they are relevant or not. You get some really unexplored ideas, something perspectives that you have not seen before. For example, I used to have this architecture majored friend who was asking really interesting questions to me, which helped me a lot. So these things like having lunch discussions and things like that really helped me a lot. So I know there's COVID and people's human interactions are becoming less and less, but trying to meet up with people, have lunch, and explaining random, really silly ideas, I think it's really essential to grow up. So I think iConnect is doing its job greatly. Yeah, that would be my word.
Now we really want to get more people, go together and see each other in person and to have more kind of brainstorming or something. Actually, Miss, you may know today we really have several peoples here. Yeah, not that many, but yeah, we have some peoples here, and some of them are this year's nomination. And some of them are last year's winner or even, competitor. Yeah. So yeah, here very nice. I think, yeah, it's a very nice go together for ICANX every Friday. So I have a questions for both of you. Because last year you are the winner, right? Yeah. So what's the secret you to win that? Because some young scientists here you want to hear. Yeah. So okay, I can ask the Young Scientist Award. You be the awardees. So you think which part is most important? You did last year. To win this kind of award or title. Okay. Can you go first?
Sure. I mean, I guess the selectors will know more because they selected us. But I feel, I mean, like the people who, all of the people who got it, they gave a very good talk, and I think they really kind of worked on problems which are very important. I felt that that was really what make a decision. I don't know how that 10 were selected from 40, but like, or from the 20 were selected from the 40, but out of the 20 to 10, it was like we all were listening to, and the talks that we had more important problem they were trying to solve, that seemed like got more attention, because at the end of the day, I think the academia has to have a social impact, and that social impact when it comes off that, so it's very important. And I actually think what Sangtae was saying, that when you talk to a lot of people, you actually know the social impact, because you are working on a very, very small silos in your research, but how it affects other people, that has to be clear from your research and presentation. So that, I think I would say, like, you should focus on. Yeah.
So Sangtae, yeah, your
Uh,
secret?
my secret would be like, so what I noticed last year is that people from very different disciplines are coming up. There will be a wide range of talks, ranging from biology, bioengineering to photonics, or physics-oriented questions, and so on. So, I mean, when there are these different various disciplines present, I think explaining your ideas to the level that anyone can understand is very important, because following biomaterials research is not an easy thing. But I think one of the candidates did a great job in explaining those things to me, who's very who knows nothing about biology and so on. So that was one thing. And then my personal favorite is sharing the flow of thoughts that you have. For example, like present some questions that you have, and then try to answer them in your presentations. That usually gives effective talks. And in terms of slide making, I think Fan is there, who was the master of slides last year. So I think he can answer more about that.
Yes, Sangtae, you're right. The Fan last time delivered the talk, even in the middle night. Yeah, at her time, and his time was Australia early in the morning, 3 o'clock. It really, really cheer everyone up because he has a beautiful slides, right? Yeah, that's give everyone very, very deep motion. I think I can tell you two guys, I be one of the committee. What kind of thing you move me, for me to voting for you? Yeah, it's because you have gone to the fundamental questions. Not only, go to the phenomena you see and the pictures and the slides and the SEM or TM, as you're going to, point out the fundamental questions. Yeah. That's the most important part from my side. I don't know how about Martin, because Martin last year was vote too. Yeah, please, Martin.
Yeah, so I would say that from the selection committee, one of the things that all of you did was simplicity. You as you work in your discipline, don't package your research in terms that only people in your field understand. You have to pull it out and make it simple. Like even what you presented today, you're showing us something that we can spend a lot of hours doing all the calculations and showing all the complexity and jargon in your field, but you bring it to everybody and say, hey, if I'm telling you about metamaterials, it's going to affect your medical imaging, it's going to affect your cell phone, but the fundamental question that we're looking at is X. When Sangtae, you talk about thermodynamics and mechanics, even for a lot of scientists who are in the field of thermodynamics, you just need to look at the stresses and you're confused. But you do a very good job of showing us how that stress is affecting transport. So it moves away from a thermomechanical question to a diffusion problem, a movement problem, a translation problem. Once people understand what you're doing, the work is very exciting. So what all the applicants last year did is, and Azari said, is to tell their story in a language that is beyond the the discipline-specific languages. And even in research, the question that Miso asked earlier on, if you want to succeed, before you speak the language of your field, speak the language of the public. And I think that's what Sangtae was getting to. Can you explain, I always ask my students, can you explain your research to my grandmother who never went to school, right? If you don't have a whiteboard, can you tell me what you do and I understand? But if you find yourself, you always need to show a calculation, you need a TEM image, then the question is, do you really understand the work? And what all the young scientists that were these last year did was they communicated their research to all of us, because the panelist is very diverse. We have come from very different fields. And so it was very easy to pick all of you because we could identify what is it that you're doing. So I would ask the other young investigators to do the same thing.
Super. Like today we already tell how we selected the winners. Yeah. Okay. Yeah. I think almost time. Yeah. Miso, can we go,
Yeah, so I have to add one more sentence here. So when I opened the application packages last year, I was so shocked because all the applicants were so talented and so I couldn't pick someone. It was so hard to pick someone and make the evaluations. So for those who are out there who were not picked as winners, so do not think that you are not winners. You are also winners. So I cannot say. So I told Alice that if I were I were the applicant last year, I wouldn't be picked, even though I was the committee. So yeah, that was the part. So I'm so looking forward to this year too. So let's move on. So can you, Martin? Yes. So we would like to deliver this virtual certificate and then to both of you, Professor Sangtae Kim. We are so proud of you. And this is the virtual certificate, and Alice will give you it through again by email. And thank you so much for being here again. And please come again more often. So and Professor Arka as well. Thank you so much for your wonderful talk. I learned a lot. And I hope to see you again. Here's your virtual certificate. Thank you so much. Congratulations.
Thank you.
So yeah. So in the next page, so here is the whole list of our 10 the winners, the young scientist awardees who belong to the first cohort of last year's. So last year and this year, we're waiting for your applications. So please, and then Martin will introduce more details to you.
Thank you so much, Miso. So again, as Miso mentioned, we do have applications for this year open. We would highly encourage those of you who are out there and have not applied, please go ahead and submit your application. We'd love to look at it. And this is how you do it. The committee will be composed. It's wider this year. There's the co-host, Miso, Christian, Alice, Paul, myself, and then we have other experts coming in, and Fulan also is a co-host. But we have other experts who are coming in to help us. So the committee is wider. And then what you need to do is you need to put together one PDF package, include your CV, a photo, and your group website. Put together your independent scientific contribution, just about up to 600 words. Don't tell us everything. You don't want 20 pages of that. Just 600 words, a summary, basically. Tell us what your outlook is and your research plan. Again, 400 words, and give us some sample publications or patents that you have filed. And then give us a name and contact information for 2 recommenders. The recommenders will write the letters Dielectric to the committee, so you don't have to get the letters yourself. We'll reach out to them. And then send all your information to this email, info@icanx.com. And we only have 2 days left, so please mobilize everybody out there. Let's make a wonderful 2022 class. And then these are the 3 steps you need. Put the material together, and then they will be reviewed by the committee, and selected finalists will be announced on October 28th. The finalists will give a presentation just like we did last year, followed by a short Q&A over 2 days, December 2nd and the 9th. And then the award ceremony will be on December 16th, 2022, with a 1,000 prize going to the winners. And after that, you get invited to give a talk like Arka and Sangtae have done today in 2023, where you can give a more detailed talk. The talk you give during the presentation is very short and it's brief, but in 2023, we'll give you a chance to give a full talk. So please do apply to the ICANX 2022 Young Scientist Award, and we'll be very happy to have you join us. And with that, I want to say thank you all for joining us. This is ICANX Talks, connecting the world and the universe. And we hope to see you next week as we continue our theme of Beyond Science. Thank you.
Thank you. Bye.
Thank you.
Thank you.
Yep.
不再是奇迹，不再是幻想，此刻正感